Hello, good afternoon. Hopefully the background noise is not too much. Is a little warm, so I'm running my window unit to keep cool in here. And ready to do some databases today. How about that? Should be good. We had a really good session last time. We were able to recover the nursery log. We had done that before, but we actually hadn't written it back to a file, which is the proper way to recover it. And so now we can create data files, which is awesome. And what we have to do next is look into building levels. So as I mentioned in previous sessions, HanoiDB is a tiered data store. It's an LSM tree, so log structured merge tree. Log structured in that the you have, how do I explain this? I'm going to do it wrong. Essentially, you write values as they come in, so they are not directly rewriting pages of an existing B tree, but instead you build a new B tree, and then that overlays the older versions of the data store. And as these things get older, they get merged together, and tombstones removed and so forth. So yeah, so let's look at what we did last time, and then get into it, and hopefully people will trickle in as we get going. Okay, so this is the commit we did last time, 2 weeks ago. We implemented the trailer of a HanoiDB data file. You may remember, hopefully, that what the file looks like is there's this trailer block, and this is so that you don't have to know everything. You don't have to put the metadata at the front of the file. You can just write the data, and the trailer contains the metadata about that file. So we implemented the trailer, and this is just has a simple constructor containing the serialized bloom filter and the root position. And then we made a method on that to encode it into a buffer. So we can write out the contents of this trailer struct into the end of the file. We also fixed some bugs. You can see here we were fixing the CRC calculation, which was preventing us from reading this correctly. Reading stuff back that we had written in the previous session, and of course we fixed some offset bugs right there, in terms of this is computing how big does the space need to be for to encode a single entry, and we were off by 4 bytes there, which was not good. And then we were just looking at inspecting this recovered nursery data, if we've done that. So going down here into the nursery file, we did this recovery, but now we're not actually returning the data because that does not go back into the nursery. Hey, Greg, good to see you. I hope you're back stateside. Awesome to see you. I'll have you next time. I'll have you on if you want. But in the meantime, we'll just I'm just happy to have you in the chat, and you can probably point out all the mistakes I'm going to make. Okay, so you're in the same time zone at least. Okay, cool. Okay, so when we're recovering, we're reading the log file. If it exists, or rather, if the log file does not exist, then we just return OK because we had nothing to do, right? And then we create a B-tree map of evacuates for the keys and entries, and this is what we're going to recover into out of the log file, so we can get it back into a data file, right? And going down here, You know, over here on the left, we were, just returning this data, but we don't need to return it this time because we're just write it back. Right, and of course we have an exceptional condition here that if there's a position and length entry that's an internal node, it should not be in the nursery log. That is a bug in the program. If we did that, just a little paranoia there. But it's good to have those little things in there in case you change something unrelated and you get a bug that creeps in because of expectations that can't be expressed in the type system. Anyway, so we're looping here, and if we get an entry, right, if we're able to read entries consecutively out of the log, then we just insert them into this B tree map. And the reason we're doing a B tree map here is that we need them to come out sorted. And the B tree map, the in-memory B tree, will be sorted by default. So the entries in the log are not necessarily sorted. Usually not. They're just in the order they came in. Okay, and then if we have no data, obviously we don't need to do anything. So we can skip over and remove the log file and return. There is a to-do here that I think we had previously. Maybe not. It's not in this diff. But we need to take this nursery data file and send it into the first level. So, hi, Isaac. Glad you could make it. So we need to figure out some of this, because not only do we need to be able to pass data files from one level into the next to be possibly merged, we also need to think about how that is structured. Now, in the Erlang version, these are processes, and they could be reached via some naming convention, but we're not going to have that sort of luxury in Rust, because maybe we'll have threads, I don't know, maybe we'll have channels and a database struct that contains those channels. That's a possibility. And then each level could potentially look into the database struct to go, hey, what channel can I send this to? Yeah. Greg's right. This will be some of the fun part. The movement of data between levels due to Erlang Rust differences. Yeah, definitely. It's going to be a challenge. But we'll figure it out together. And I'm sure that the first pass that we do is not going to be right. And that's okay. But we can figure out what we want to do as we go. Okay. So we may need to find a way to plumb through the database struct, and we should probably make sure that it is a something that we can pass immutably. And if there's any internal mutability, or if there's any sort of pushing data into another thread via channel, or something like that, we need to have a smart pointer around that, because we're going to have this database struct available to multiple threads at the same time. Okay, so now we're talking about probably arc mutex or arc read write lock, and it's getting messy already. So we'll need to think about that. And I'm going to have to learn some things, so maybe we'll learn them together. Unfortunately, I've done a decent amount of Rust, but all the stuff I've done pretty much has been async, so using Tokio, and running a server or running something that uses Tokio as a client, or it's been in the browser where there's no threads. So we're gonna have some challenges there. Maybe we'll come up with something interesting to figure this out, or maybe we can just do it single threaded at first, but that'll be kind of interesting to figure out. We may have to have a queue of commands or something like that, and things get pushed into this queue and there are merges in the middle, etc. Okay, so Yeah, so that was the nursery and the recovery. Looking at the writer, we added just a little simple function to determine if this is similar to a pattern match that we did in the Erlang side, where it's like, hey, if there's only one entry in this inner block, then we can just discard it because it's no longer the root. Okay. Obviously, there's some type changes here because the node size needs to be encoded in the trailer as a U32. We're using last node size as a U32 instead. And then, yeah, and then we remove some unnecessary stuff. We don't need to keep the file name around. And then the close writes the trailer. You've seen this last time. Let's see, and append to block. Right. So I think I want to look back at the Erlang code, make sure we didn't miss anything in the writer, because I have a feeling there's something, archive nodes or something that we didn't look at. No, this is the bit that we handled, right? So archive nodes does the final writes on the file. Yeah. So we did handle that. Okay. Thank you, Isaac. Yes, I did a lot of talks in the past. If you do enough Googling out there, you can probably find me in a much younger state talking. The other day, actually, I went looking for one of my talks from Strange Loop, because I only spoke at Strange Loop twice, but it doesn't exist, at least as far as I can tell. I know Strange Loop had some changes there in the middle, like maybe they're originally on Vimeo, I don't know, but it's not very Googleable anymore. So that was unfortunate. Okay, so yeah, let's go back up here. Right. I agree with you, Greg. And this is something I'm hammered. You want this part to also surface the natural back pressure of Hanoi. That's the point of having writes push down in levels a set of steps before returning. Right. So we need to figure out, and maybe it's a queue. It will limit our throughput potentially as compared to the Erlang one. But at least then we would be operating over only one set of work. All right. Well, let's maybe sketch out some things here that we could do. So I'm just going to write them up in the README. So options for handling merge work, because that's where the crux of this is, and there's some problems here that we need to solve. So problems we need to solve. We need to pass merged files. So this includes the nursery data into the next level, right? We need to trigger incremental merge work across all levels when we reach a threshold. And that was, if we look at the nursery, I can hide this shell for now. Right, so this stuff, right? We need to make each level do a certain number of steps. So how steps are defined in HanoiDB is I'm not as aware of, but there's this merger thing we'll probably end up looking at. Let's see, ABX is last level options. Right, so we'll need readers, and we've got a writer that we can add. And then, yeah, this is about merging up to 3 files, I'm guessing. No, this is merge into this. Yeah. Okay, so this is about merging 2 files. Right. Okay. So there's this hibernate scan function. What it's looking like is, okay, garbage collect, because that's a good time to garbage collect right before you're about to sleep or wake from sleep. And if you receive a message for, implement this many or increment this many steps in your merge process, this is, I guess, who sent it, and then how many steps to do, right? Okay. And let's see. I'm guessing this scan, there might be some kind of metadata file that is keeping track of where you were in the merge. I'll have to look into that. But yeah, so start a scan, go from A and B into out, and then all this stuff. So yeah, okay. Let's look at the scan function. Yeah, my Erlang language server is still not working. Okay, so here's a, do we call receive scan anywhere in here? No. Okay, there's some plain FSM goop in here, but I'm guessing so that's so we didn't have to use gen statem. Yeah, or gen FSM. Gen statem's the new one. This existed before gen FSM, or this existed before gen statem, which is the newer, more flexible one. Okay, so if we have scan, okay, then n is okay. So if there's no key value pairs from either, then we just say done. So this is sort of probably a tail recursive loop. Yeah. Okay, so then it's like read from A. Okay. And if you get the end of data, and you close it, and you scan B only. Okay. Otherwise, you're adding these. Okay, and then it's like, okay, so this is if A is empty, read some key value pairs. And then this is if B is empty, read key value pairs from B. Okay, and if n is 0, you just say you're done. Okay, so what's not clear to me is if neither of these are empty. Okay, so now we're going down here. So now you're comparing the keys and values there, and you are, if A is less than B, then you add A to the file, right? And then if A's key is greater than B, then you add B to the file, and so forth, and you're popping them off the list, right? And then I assume this is the case where they're equal, right? And then you just arbitrarily pick one. Sure. Okay. And then it's tail recursive. So down to where, let's see. was this step? So let's look at this step function. Sorry for this, folks. We're just learning here. Step and 2. Okay. I'm guessing if this is where they're equal, yeah, you arbitrarily pick the B. I wonder if that's because the B will be written later than the A. Probably. That's probably the case. Okay, so let's go to step. Okay, so this is just counting down the number of steps. So that's the termination condition of this this scan loop. Remember, this is, you know, Erlang tail recursive. So we're calling the same function at the end, and then there's also this companion function scan only, which is going to probably just scan the one file, right? Okay, and it's doing a similar thing there. So like if n is 0 or less than 1 for whatever reason, and non-zero, and there's no more keys, then you're saying you're done. Yep. Yes. Thank you, Creston. Wow, I didn't expect to see you in this stream. Yeah, and that makes sense because you're writing the A file first and then the B file. And as they're merged together, then you know, the B file, if it has the same key, it'll override the value from the A file. Makes sense. Okay. Wow, getting all the original authors in my stream. Also, it's late, very, very late, Creston. Glad you could join though. Okay, so yeah, and this is just when it reaches the end of the data in both files, or it runs out of steps. So if it reaches the end of the data in the files, it just terminates itself. Okay, that's fine. So let's look at this receive scan only, and I think this is probably the last thing we need to understand about this file. Okay, so it's just waiting. Right, so it's waiting for a message that's saying, hey, do some more merging. And then if it gets any other messages, it's going to do some, this is Erlang stuff that probably won't apply to us. But if it's not doing anything, it's going to wait until it hits this timeout, at which point it's going to go to hibernate. So this is a memory saving operation. So if there's no work to do, it makes sense to hibernate this process, and collect collect information about what was being done, and save it. Okay, so that will not apply to us, although this timeout is interesting. And we should probably look at what the reader serialize and the writer serialize do. So let's jump down there. Okay, so it's just reading what is the current position in the file and closing the file, and then returning something that can be, you know, safely serialized. A file handle can't be safely serialized because that PID could go away, right? And file close, you know, kills the PID that represents that file. Anyway, so, and then here it's opening there and then like resetting to a position in that file that was the serialized position from up here. That makes sense. Writer, let's look at serialized there. It's not so important since we're not going to have hibernate in Rust, but there might be something there that we want to do that's similar. So I think it's good to read and understand this. Okay, so if we're writing into the file and we've got the bloom filter and the position. Okay, so I'm guessing this is just EVF. This is an interesting function. Okay, so this is just saying like, what is my position in the file if it equals this position? I don't know what this flag does. I'll have to look it up. But otherwise, then, you know, you can't serialize. And then it's like, close the file, and there's no index file in there. You know, toss out the bloom filter, except we're going to serialize it. Right, so it's turning into a binary and recording which type of bloom filter it is. Yeah, it is definitely to reduce memory consumption while sleeping, for sure. Cool. Right, and the deserialize here does something very similar to what was done in the reader. You know, decode the term that was serialized, turn the bloom filter back into a data structure you can manipulate, open the file, and then yeah, and then I'm assuming this is resetting the position. The open ops state.ops. Interesting. Okay, so, you know, we're going to have readers and writer. Well, we don't really have a reader in the same sense on the Rust code that I've written so far. We've written together. But we do have a writer. We sort of have a reader here, but it's in pieces. And I don't know if we need to reify that concept yet. But we definitely need to have an idea of a merger. And the question in my mind is, let's start to think about how this forest of trees can be constructed. So let's make an, you know, I started to write in here. So let me sketch some potential solutions. The first one I'm thinking of is we have a DB struct, and it contains the nursery, and it's going to contain some collection of levels. And I think the levels have to be something like it'll be something like a hash map of U32 to level, whatever we define a level to be. Except that, now this is fine if it's single threaded, so we'll probably just pass this mutably around. The other possibility is that we have a DB looks more like a nursery, which is a channel of some sort, and maybe the nursery is just like the first level. We don't know. And the levels are also a hash map. And I say a channel. It's possible that the nursery needs to be. Let's, for sake of argument, let's say it's arcmutex. I don't want it to be that, but like, yeah. And we'll look at threads and things. So the hash map, the levels is going to be probably, and this is where, you know, the borrowing in the smart pointers gets a little wonky. I'm thinking it's going to be an arcmutex hash map level, and this is actually a channel of some sort. I'm using channel there. It's not actually a type. There is probably, I've been looking in Elixir, see Rust. So standard sync, multiple producer, single consumer. It would be like a sender. So let's just say that's a sender. Now, we could use a sync sender. Which would block and provide us some of that back pressure that we need. There's a question about when do we spawn threads, like, because there should be, obviously, when we need to create one, we'll be spawning a thread that owns the receiver, and maybe this is a sync sender, maybe this is a sync sender here. So it could look something like this. Maybe we start with the single threaded version, and then if we need to do the multi-threaded version, then we will go there. So basically the logic for when to trigger merges will be a combination of, you know, the nursery and the level, and we'll make the level struct. Okay, I don't know if we'll commit this, but we also have a to-do. Yeah, we did all that. Okay, those are no longer to-dos. Okay, so let's make a merger. And this we will need to do. Let's see, what do we have here in writer? We're gonna need some of the same things. Yep. Do we not use that? Okay. Okay, I don't know that we're gonna need all that, but let's pull it over here. I actually don't think we're gonna need entry. We don't need trailer necessarily. We don't need tag end or compression, not yet at least. Okay, we may not even need write, because the essence here is we use the writer. So we're going to need create writer. Okay, and then we're going to make a struct, which is the merger. And we'll get to levels, I think, later, because there's also an essence of, or an element of, how do you read from a level. And it might be a thing where we have the level has some fields that are potentially optional, like, is there an A file, is there a B file, is there an X file? X files. So it's gonna have an A, and I think that this is going to be an entry iterator. Is it not? Oh no, we can do tree. We can use tree because this is the file, right? So not entry iterator, tree. And this is a writer. And then we're gonna need so I think I need to see HanoiDB merger start, where that's called from. Right, okay, from level. We should be looking at this file too. Okay. So yeah, it starts a merge. Okay, and this is that size is how many keys? Okay. And okay, and this is about, so the levels are almost like a, this is it the last level? So if there's no level greater than it, and then there's, you know, whatever those options are. Interesting. Okay, where's this called from? Begin merge. Oops. Hmm. Check begin merge then loop. We're gonna have to look at this file. Oh my. Okay, and it's all within this file. So begin merge must not be exported. Must not be an exported function. It's another plain FSM. Yep. Okay. All right. So level. Right. Okay. Initialize is the thing it does right away. Okay, so the lookup, these are all like the I want to find a key in a particular file type things, which we did in tree, I believe. So we did get, you know, yeah, is this in this file? So it's a matter of in the level, it's going to look at, does it have a B file? Look there first. Does it have an A file? Look there second, if it's not present. So it's sort of probably like a chained thing. Okay. Okay, so there's a lot in here. This is interesting. So when it's starting up, it's constructing file names for each of the potential files that could be open. And it's removing the X file, which is the file that was being merged into, if it's present. And then there's these files that are used for folding over keys. So if you're trying to scan, it does it with hard links so that you can continue to write while your scan is going on. Okay, and then this M file has to do, this is probably a file that's ready to be promoted to the next level. So this, let's see, if this M file exists, okay. Okay, so this is a case where a merge completed, resulting in a file that needs to stay at the same level because the resulting size is smaller than or equal to this level of files. Okay, so okay. So it's where you get push. So A and B probably come from the something from the lower level being pushed up. But if you combine the two and they're not big enough to go into the next level, like if they're smaller than the current level's threshold, then you keep the M file around. I'm guessing that's what this is about. Okay, so file rename. So this is saying, okay, the merge completed. So there's this M file. You delete A and B, right? And then you rename it to A. Okay, and then you open the file you just renamed, the new A file. Okay, and if there's a C file, then you rename that to B. And then you've got your A's and your B's for your readers. Okay. So then you go into, check, do we need a merge? And then go into the loop. Otherwise, no loop. Just loop. Okay, and then there's this other case. So if there's no M file, then if you've got a B file, then open A and B. And then potentially C. So if C exists, then you open C. If not, then it's undefined. So I guess the idea is if you have an M file, you're going to have an A, or if you don't have an M file, you're going to have an A and B? Does that invariant hold? Oh, but this one is saying if you do have a B, so you won't have a B unless you have an A. Okay, and if B doesn't exist, then you make sure there's no C file, and then you just open A. Okay, this is kind of nested cases. We need to look at this function. Check, begin merge, then loop 0. Okay. Okay, so this is the one that's is calling begin merge. If there is no merge PID, right? And it's monitoring that so that if the merge PID crashes, you get a down message. Okay. All right, so this is saying if there's a C file, so that's this case, you need to be targeting a file of twice this size, twice the size of the current level, right? That makes sense because you want that to promote to the next level. If there is no C file, then you can, I guess, merge. This has to do with merges. Okay. And let's see here. Okay, so this is probably merge for the before you are actually starting up the level. That makes sense. That's why it has the 0 on it. And this one is basically the same stuff, except that you're calling merge. This is going to be called from somewhere else, I'm sure. Okay, and if there's no merger defined, then you want to start it when you call this function. Okay, so here in the main loop, if we get a call from lookup, then you're going to look, hey, look at that list of do C first, then B, then A. And then I guess next is the next level, right? Okay, that makes sense. Yeah, and we'll look at do lookup. That's interesting. Okay, and then if it's not found, you send not found. Right. And so this delegate is interesting, and that's like, I guess, passing on the request. Yeah. So it's possible that if you're trying to look up multiple levels on the Erlang version, or you're trying to look up a key that may be in a deep level, you're going to try at the top, the youngest level. And if that doesn't work, it's gonna say, hey, is there a next? Well, delegate this request to that. So send this request to that process, and it'll receive this, and go look for it in its stores, and so forth, as long as there's a next. And right, and this is similar, except you can pass a function. Okay, so inject, this is the thing we saw in the nursery, right? This is receiving a file. It's like, hey, I have this file. that I merged, or I'm the nursery and it's my first file. It's a little baby file, but it's complete, and you need to take it over. So that's what this inject is, and it's looking at the state and saying, so if there's no state C, so if there's no C file, right? They're going to look at, do we have A and B? If they're both undefined, this file becomes file A. And this little thing here, by the way, is record syntax in Erlang. If you're not familiar with it, this compiles out to be an index. Index into the tuple. Okay, but in this case, if there is an A but there's no B, then it becomes the B file. Otherwise, if there is an A and a B file, it becomes the C file. So then we rename that file. We reply OK. And then we open it. And here's this check begin merge then loop. Right? So if it was set to B, you'll have to look at what that random thing does. But if it is, oh, okay, that's random reads. Right. If this is the B file, then it's like, check, do we need to merge? And the set element here is updating the state with, this is the file that we opened. Otherwise, okay, so that's interesting that if it becomes the C file or the A file, we don't check to begin merge. Now, I'm assuming that if there is an A and a B already, then the merge process may already exist. So I think that's what we did here in this 0 version, right? Yeah, so if both A and B are undefined, the merge process already exists. So C should not trigger another attempt to merge. Okay. We're learning. This is just implementing how many are unmerged from this level. Okay, so propagating knowledge at the max level. So interesting. All right, so begin incremental merge. So we'll need to look at this do step function. Okay, and so here's the handshake. So if it's saying begin incremental merge and then await is like, I'm going to wait until you're done, right? That makes sense because none of this is synchronous in Erlang. Like, it's all asynchronous. So you have to create little protocols of, I'm going to send one message and wait for a particular kind of message back to create synchronicity. It's more like barriers and less like synchronization. Anyway, okay, so if we're not doing any merges, I'm guessing that's what this is about. Just send OK, go back to the main loop. Okay, we're definitely gonna have to look at this do step. Okay, so this do step is probably like, this is creates a process and then it expects to be replied there. Okay. Okay, this mref is a monitor ref, by the way. And that's just, demonitor. If you get step done, then that process is about to quit. Right? Because we saw that in the merger. It says it sends this step done to the level that started it. Okay. Yeah, and here's the down. So if the merge worker died, clean up state. Okay. Um, in some ways, I wish these were handle calls and handle infos. But it's okay. It's okay. There were probably good reasons at the time that this was not a Gen server or a Gen FSM or something. Okay, so there's a lot of messages going on here. What I want to get to is this do step function that we saw. We can skip over lookup. Where is do step? Okay. Okay, so step from is either process or undefined. So previous work, this is how much work you've done already. What's the step size? So this is like, hey, do 256 steps or something. And then the state of the process, which is just a record. Okay. So how much work left? Okay, if the B file exists, basically, and the merge process exists, right? So it's not undefined. Then you're going to pick the max of 0. So obviously you could do 0 work. And the difference between the size of the next level and how much work has already been done. So I'm guessing that the step here is like 1 key. Or in the case of where they're equal, it's 2 keys. And I think we saw that in the merger. It's like counting up, right? Okay. So then you've got the work unit is the step size. So the max level is the max of either the max level across the entire database. So how big can a single one be, or the current level, which I'm assuming that if we hit max level, we're not going to create levels above that, so these two will be equal. Okay. So depth. I'm getting lots of blinky. Depth is max level minus top level plus 1. And top level is defined somewhere, probably in here. Yeah, top level 10. But top level meaning the smallest level. Okay. So, whatever the max level is set at, this is basically... Okay. Okay. So at bigger levels, the number of keys you're going to process is going to scale. So if you're saying do 256 steps, let's say you're at level, let's say your minimum level, which here it says top, that's a little bit confusing, but your minimum level is 10, and you're at level 12. So this is going to be 12 minus 10 is 2 plus 1. So 3. So you're going to do 3 times whatever was given as the work unit, so the step size, right? So if you're doing, if you said do 256 steps, yeah, bigger levels are below. This is true. It's like it goes down, right, rather than up. Oh, directions. Why couldn't there be left and right levels? Anyway, I'm digressing. So if we're at depth 3, so like we're deeper in the storage, like this is colder data, right? Then we're going to do 3 times the amount of work that was requested. If we're at the same level, we're gonna do 1 times the level. So like if we're at level 10, if the min level is 10, and then we're gonna do this is gonna be 0 plus 1. So we're gonna do 256 keys. We're gonna process 256 keys. If we're at level 11, we'll process 512 keys. If we're at level 12, we'll process whatever 3 times 256 is. I can't be bothered right now. But so, and then it's like it's like Towers and Toy, right? In order to move the ones that are on the bottom, you got to do more work. Yep. So more ways than one, not just the way the files move around. Anyway, so then we're computing how much work units do we have left. So what is the maximum between like the total work we want to do and how much work we've already done? Okay. Right. Well, that's fun. The goal was to offer a less variable latency option for merging, but this heuristic doesn't work when there are aggressive deletes. So if keys expires or are just massively deleted, which is the thing that happened in React from time to time, especially if you have the expiration turn on. Okay, so right, so you could choose between fast, which is where's work left here? Okay, so you would choose the minimum between this computed thing and how much work could be done at this level. Excuse me. Okay, so the predictable here, this could have reused total work, but okay, so this is like if you don't have okay, so if the work left to do, so this is the maximum work that could be done in this level, right? Subtracting how much has been done already. If that is less than, the desired amount of work, depth times work unit, then you pick the minimum of those two. So this would be like, don't do all of work left here. Do just work unit this time around. Now, if work left here is greater than or equal to this total work, then you pick the minimum of the total potential work, or yeah. What's not clear to me, and I think we'll have to learn this in a bit, is what's the difference between this previous work thing that's passed in versus the work that has been accounted for in the state. Because that seems to be the crux of like what should be done. Okay, work including here is previous work plus work to do here. So this is like, here's how much we're about to take on. Yeah, I wish you ran to name these in the past. Too much clearer, not you, man. Oh, probably only if I went in here and go, guys, what the heck is this? But now it's 12 years ago, and so we're relearning it together, right? Okay. Yep. Hey, naming is hard. I name things just as badly as anybody else, so I don't claim to know what's going on. Okay. So then, okay, so if there is a next level, Ah, okay. So it's saying, hey, um, I'm about to do this amount of work, and here's the step size that I was given, so why don't you go do some too? So this is the cascading merge stuff. Okay, so I'm wondering. So if we go back to where, let's go back to the main loop real quick, um, and find that step level call. Right. So this is work done at a previous level. Okay. So interesting. So this is not. This does cascade, but deeper levels don't do as much, because if a lower level is about to do a bunch, then it's going to say, hey, I took this many steps. So that's what the difference is here between this and what's in the state, right? um, so this is like how much work was done by younger generations. um, okay. And then the step size is like how much, how much is this incremental piece of merge work supposed to be. Okay, that's making more sense now. So this count is like accumulated up and passed down through the levels. Good thing we didn't write it. Somebody needs to talk to those authors and give them what for. Okay, so um, we've got that's really interesting. Really interesting. Because this, if I were to just recontextualize this process in Rust, it feels like what would happen is this would be a loop, and you would be tracking how much work is done in each level as you iterate through the levels that exist, and you would pass along um, that as some kind of mutable variable that you change in the middle of the loop, or you could use reduce or something. But yeah, okay, that's really interesting. Okay, so then we're going here. If there is work to do, um, then we monitor the merge process, right? Which I thought was done already, but it's fine, whatever. And then we're telling the merge process to do a step of this many. And we already saw what the merger does in that case. And then we've got the monitor. Okay. So delegate ref. Okay, so if there was no next level, right? Or this plain RPC doesn't return if it returns undefined. Okay, so if there's no next level and there's no merger, then we just say, yep, we did it. Otherwise, you go into the main loop, and now we've got a reference for this, right? A reference for the reply from that. And then we've got who called us to do a step. We've got the merge ref, which is monitoring the merger process. And then here's how much work was in progress. Okay. I think that is really, really informative. I think we need to go back to the main loop because there are some other clauses of that are of this receive that I need to look at. Okay, so we're going to collapse a lot of these. Okay, so begin incremental merge if we just saw these two things, if they don't exist, so if there's no next level and there's no merger, this is not exactly the next level, but that's like waiting on the reply from the next level. Okay. So begin incremental merge. Okay. And we're going to have to search. I actually don't know if that's being used. Interesting. Probably is, but okay. So if we get a from and we're not already doing work, then this is what we were jumping into before. So step level. We also did it here in beginning incremental merge, but we're saying, hey, we've done 0 work so far. Okay. Yeah, that's just a call from level. Okay, so we're getting step done, and this is some stuff we were looking at before, right? This is the merge process. So this is the monitor on the merge process. Remember, it's replying with the monitor ref so that we can pattern match on it. And it's saying, hey, my steps are done. Then okay, and so then it's going add how much, because remember we recorded how much work in progress was going to happen, and then add that to the total amount of work done already, and set work in progress to 0. So that's what this is about. And then if there is not a next level that we're waiting on, then go ahead and reply. But if there is, then we just leave it. Okay. It'll be interesting to see like what that actual reply step. Okay, what does that do? Let me jump to that real quick. So I think that's. Oh, it's just saying step okay. So if we go back to main loop, there should be a clause in here that's like step okay. Yep. Okay. So we'll get to that in a moment. Okay. Right. So this is saying the merge process said step done. We don't need to monitor it anymore. And here it's like, oh, well, we got this message, but we're no longer monitoring it. So, yep, bad message. We should exit. That's just protocol invariant there. Okay, and here the merge worker died. And so, or it just finished. So there was maybe a race. I think, though, if it died normal, we should have hit this one. Yeah, if it exited normal, we should have hit this one. Maybe there was something else. Maybe, who knows. Okay, and then it's like, hey, we don't no longer merge process, and there's no work in progress. Yeah, so the lowest or the biggest level is the one that sent the reply. Yes. Okay, so this one is like, we got a reply, and that reply was step okay. This came from the a deeper level, a bigger level. And then we're expecting this to be the reference that we got out of that call. And okay, and then our merge process should have finished. Okay, and then it's, yeah. Okay, so this applies when we receive an okay from the next level, and we have finished the incremental merge at this level. There's a question in my mind about what happens if our merger takes longer than the deeper levels merge. Maybe we'll find that down below. But this guard clause here is basically saying, you know, we have to have this, but our we have already handled the step done message, essentially, or we're not merging our own level. Okay, right. So that's what this is saying. Applies when we receive an OK from the next level, and we've finished incremental merge at this level. Right, and that's just, yeah. And it's saying reply to our caller with OK, so it's going to send step OK to whoever called it, and so forth. Let's see, close. Yeah, this is just shut down. Destroy is probably a bit more. Yeah, this is like delete the whole database, I'm guessing. Okay, and then there's folds, which we don't care about right now. Range fold. Range fold. Okay. So this is interesting. This merge done thing is... We're going to have to look at this a bit deeper, because we do want to understand the merge strategy. Okay, this is like merge done 0. Like there's no more work. What I'm not seeing is another like Okay. Then we have stuff here about moving the files after the the merged file has been accepted by a deeper level. Okay. Lots of handling exits. Things about folds. Okay, we're not going to be able to tackle all of this today. Obviously, it's already 75 minutes into my stream, and we mostly done reading code. Okay, so one thing about sorry, I'm just getting my head around all of this. We obviously need to do like something generic around merging files, and like these are just arbitrary. But we need we're gonna need some information in here. Let me go ahead and make it a mod merger. We're obviously going to need something in here about like doing incremental work. And computing how much should be done, and tracking it, right? So this would be similar to the merger process. Oh, okay, so those are just hints. We saw that random earlier. This is just a hint on how am I going to read the file. I'm going to read it sequentially. Okay. So I think we need to start probably with, we've got two files. And we want to scan them from the first key to the last key. Not all at once, obviously, but we want to, look at those two files and pull keys out sequentially. So, I don't know. Let's do some pseudocode, and then we can figure out how to build out the rest of it. So what I want to do is basically these clauses. I want to look at, let's do like one step, right? Like let's compare two keys and add whichever one is smaller to the writer, while keeping the other one there. So we need right. Yeah, Creston is saying merge is really tricky. The idea is it needs to progress enough that we avoid the worst case cascades. So it's essentially by the time the nursery is full, the top smallest level has room to inject a whole level file. Right, and I'm guessing that's why in here where it's computing how much work to do. Right, it's going, I need to increase the amount of work I do in deeper levels, so that it keeps up. That makes a lot of sense to me. Okay, but yeah, and recursively by induction going down to bigger levels. Right, absolutely. Okay, so I want to do, and I think here's what's tricky, is we have this, but actually what I want is maybe not trees. Maybe it's, I don't know that we ever, so we have an iterator over blocks, but we don't have an iterator over the entire tree. Now we do have in single key lookups in get, right? But what we kind of want is something that will let us iterate over the entire tree. So similar to what we did on block, we have entries. Let's just say entries and self, and it's going to give a tree. Let's make a tree entry iterator. What do we do on block? And we'll do something similar to this. Well, it's going to have a lifetime of some sort in it. So let's just do tick underscore. We don't know what it's going to be yet. But what I want to do is be able to traverse the blocks so that we can take entries one by one out of the file, right? Because, here we're going, we get the root block, and then we're iterating down to, or we're going over the entries in the current level. Now it's funny, we did something similar to this when we were doing Berkeley DB, right? Because we looked at Because you can have inner nodes, you can have leaf nodes. And if you're at an inner node and you want to iterate through each of the levels, or you want to get down to the keys and like iterate through all the keys, you need to keep track of what inner nodes you were at. And so we need something kind of like a stack. Now here we were just doing it brute force, right? We're like, if our block level is greater than 0, so if it's not a leaf block, then we're iterating over the entries, taking while the taking from the entries iterator while the key in there is less than the first key we're looking for. Or sorry, the first key here is this logic is hard to explain. Basically, we want to find the first posilon entry that could contain this key, and then we take the last one. Right, and then if there are none, so like if it is before the first key in the database, then we return none. Otherwise, then we've got a block, and then we continue the loop. And then once it's at level 0, then we iterate over the entries in there because they should all be key value entries or tombstones. And yeah. Notably, this uses find map on entries, and it doesn't bail early. if the found key is greater than the key, which we should do, that's okay. Anyway, so we need something that's kind of like, and we'll make a struct for this. And I think what we'll do is we'll just do tree entry iterator new, and we'll pass self, and it'll borrow stuff from this. Okay. And this is going to be so the tree is we're going to borrow the tree, right? And then we're going to have we're going to potentially run into some problems here, but I think we'll have levels. It's going to be a vec of entry iterators. Okay. So okay, so we're going to do self tree is that, sorry, and then levels is going to be a vec new. Okay. So where it's going to get tricky is going to be We have to impl iterator, right? Iterator for tree entry iterator. Okay, so item is going to be entry, just like we did for entry iterator. We can get down here and find where that is. Where did I find that? Right. Right, so this returns entry, and basically we're going to be taking from these entry iterators, but we're not always going to be returning them, because if we get a poslin entry, that tells us we need to be getting the block that represents that and push it onto the end of our stack, and yeah, and so forth. Okay, let's go back up to here. Okay. Right, so the idea here is that we will you know, it's interesting. Maybe we even start with the root block. And maybe we don't even need the tree. Because they'll all be borrowing from the tree. Although we might need it to be able to get the next block. Yeah, because it doesn't, there's no way to go from a block. Right. It doesn't go, there's no way to, we don't have a way yet to go from a block to another block in the same file. Although we could. I think let's keep going forward with our tree iterator, and then we'll see what we can do. All right, so this needs to be result self root block. And I need OK. Okay. So, okay, so our very first thing is we want to get to the next, we want to get to the leaf node. If we're not at a leaf node, we want to get to a leaf node so we can be iterating over the entries, right? So if we're at the root block, it might be an internal node. Probably is. And so what we need to do is I'm going to do this very, very naively at first. And we're going to do okay. So if we have one, if we have an iterator in there, obviously if there's nothing in there, then we've completed and it should end, right? It should end iterating. This is the hard thing about lazy iterators. You have to think about like all the intermediate states. Okay, so we get the last level in there, and in this case we're starting at the root. If so, then what we want to do is we'll probably have a loop in here, right? Where we are and we'll break out of the loop. So if there's no level, right, we will this could be while let. And let's not refactor it like that yet. What I'm thinking about is we need to check if this iterator has anything in it. Okay, so let's do the naive one. So if we say if level dot next is sum, and this is going to be an entry, right? And this is entry key value, and we don't care. Then we want to return sum. Actually, we can just do entry, right? Except you're gonna make me put curly braces around that. Fortunately, I did a little like spelunking in Elixir this weekend, and so I'm really confused about which arrows it is. Thanks. So great to be polyglot. Okay, so right, I know there's not gonna be none. Okay, so if we have some, but it's entry deleted, right? We don't care. Like, well, here's an actual question for Greg and Creston. Do we care? Should we be pushing the tombstones? Should we be returning tombstones? It's an interesting question because I think maybe we do. Yeah, let's maybe make the case for if it's, we need to handle this, but what we need to handle is if it's a poslen, right? Because this is where we need to in this case we need to get a block for this and push it onto, and this is where we may run into cases of overlapping borrows, but whatever. We need to push it into the levels thing, and go next. So this is going to be a continue, right? And we're going to do self levels push from start length, and this is going to be tree.file. Or can we just do, we can do this, right? Block from Poslin entry. And I've lost it. This file's getting too big. But if it's none, we need to pop this iterator off. And then if we've reached the root and there's nothing left on that one, then, you know, there's no more entries, right? Okay. So this is actually, we want tree block from self.tree from Poslin entry and what's wrong there? Okay, fine, borrow it. Don't care. And then we need to turn it into an option entries. Okay. I'm just going to break this out so that it's clear what that is, and then so I can put a name to it. And then we're saying we're putting a new actually I don't need to reassign that. So okay, we're putting a new we're pushing a new iterator onto this set of levels, and then we'll go back. So this is how we're recursing down the tree. And then as we exhaust one, we'll pop it off. So if there's none, then we're going to do self.levels.pop. And I need to see vec. I need to see there's pop. Right, so return the last element from the vector, or none if it is empty. Now we know that there is something here, so this is a must use, so we have to assign it to something, and then we continue. Now here, oh well, if it's empty, we'll hit this. Last mute will return none. This question mark will return none, and we'll terminate. Wild. I was actually thinking that was going to be harder. But this will never infinite loop, because if our set of levels that we are iterating through are empty, we'll return none. If we hit a Poslin entry, then we will push its iterator, the iterator for the thing that points to, into our stack. If there is an entry, so we got an entry and it's not a Poslin entry, then we just return it. And otherwise, if there's nothing left in this iterator, we need to pop it off and go to the next one in its parent iterator, and so forth. So we've got a recursive thing going on here with the stack. Okay, that feels way better than I expected it to. It just goes to show sometimes you have to start with the most naive thing and go, I'm going to meander my way to the solution. Okay, so now we should be able to, assuming the compiler is happy, which it looks like it's not. So let's find out what's wrong. Right, okay. So this is, let's say that's result. Let me just return. Yeah, fine. We don't care about the merger. We'll fix the merger later. Be an acquisition. All right. So one of the consequences of this is that we are going to, when we iterate over a tree, we're going to iterate over tombstones. And I think that this... correct me if I'm wrong, Greg Creston, but it is necessary to keep those around. Unless you are merging in the max level. Because what you want is if you deleted that thing, you want the deletion to mask any previous versions of that key that might have been in deeper levels, right? So it appears to the caller, hey, it's gone. Even though on disk, like, hey, that old value might be somewhere deep down in the trees, in the forest, right? Yeah. Okay, so going back to the merger, I think what we can do now, the merger is not going to have a tree. It's going to have a tree entry iterator. Because and I actually think that this is fine. I don't really like this, but I think I'm going to have to give those different lifetimes. Do I? No, because they're going to be together here. So... the lifetimes of those need to be equivalent. And maybe we don't need tree. Okay, back to our original goal here, which was I want to do one merge step. It's going to have to take mute self, right? And my goal here is not to do the entirety of the like swath of merge of like steps that we want to do. I just want to do one, like compare the two keys and write the winner to the file. Okay, so what I need to look at is iterator. I think what we need is peekable. Because what we want to do is we want to take one without advancing. Interesting that we do next if, like we could do, okay, so peekable is a method on iterator. So I think that we want to import this. And this is going to be peekable. Right, because we want to make sure that we can advance them independently. Okay, so we could say a next is self.a.peek, right? Let b next self.b.peek. And we didn't implement ORed or partial ORed on entries, and I'm wondering if we should do that. Because then we could go if a next less than b next, right? But we do have key. We say if a dot key, a next. These are both options, though. If there's nothing left in this iterator, then how about we do something like this? And if they're both none, then we have no work to do. If there's some a and none, then what we do is we do self.ax and this is a writer. We do add, right? Add a. And let me here. We're going to split it like that because I want to look at this. This returns result unit, right? So this should return result unit. And we'll just self.add like so. But we also need to discard that. From the iterator, so we need to advance it. Okay, so peak returns a reference. Okay, so actually what we need to do here is go because we need this to not be a reference, which means we don't actually care in this case. So we need to do let entry is self.a.next. And honestly, we've already asserted that it's going to have one, so we can unwrap there. And then let's do self dot x dot add entry. And we'll put question mark. Okay. And actually, we don't need question mark because that's the result, right? And this should be okay. There's nothing to do. Okay, and then if there's no A, but there is a B, then we need to do basically this, but with B. Okay. And now here's the kicker case. If there is an A value and there is a B value, then what we need to do is if A.key is less than B.key. I don't know why that's being weird. Oh, I need fat arrows, not thin arrows. I don't know what's wrong with me. Okay. So if A is less than B, or we could do comp, because they should be comparable. So A.key comp B.key. And this is going to return ordering less this is getting a little crazy here, but what's wrong with that? Why is it not? So one thing that we can, all right, we can if we can do this because we only want to keep A because we know B is newer, right? That was one of the assertions that we were making in the Erlang code. What is going on here? What did I do wrong? Thin arrow, that's what I did wrong. Okay. So we can actually do let entry is this, right? And then self.b.next.unwrap. Okay, so okay, that was complicated, and it's like, all right, here. Okay. Yeah, never used. Don't care. What's wrong? Yeah, fine. Okay. So what are we doing here? Okay, if both of these are exhausted, then we have nothing to do. Now, one thing that might be interesting here is and there's something subtly wrong, actually. Okay, let's think about the simple case. So if A is less than B, then we know that we want to, and this is where I may bring back the match, right? If A is less than B, then we know we want to take A and add that. Otherwise, what we want to insert is B, but we need to handle the case and let's extract this into a variable and rename that. Rename, please. Rename symbol, order. Okay, so if A is less than B, we definitely want to insert that one next. But if we want to, in all the other cases, we want to take B. The other possibility is that they're equal. Equal, then we want to consume the value from A. Otherwise, otherwise we leave that unadvanced because this was a peak up here, right? I wish there were a better way to express this, and maybe I'll turn this into a match. Yeah, let's turn this into a match. Okay, so if it's less, then we want this. If they're equal, okay, if it's greater, then we want this. If they're equal, then we want to do discard A because it's older, right? So we want to return B, but we want to discard A. Okay, I think that's a little bit clearer. Okay. That's better. Right, and I think that's a good place to stop today. We are going to have to do the rest of this, but like we kind of have a little micro view of what we should be doing to merge two files together, which is we iterate through all their entries, and then we do one step. Now, there's one other bit here, which is we need to not return unit. We need to return how many steps were taken, because in this case, there's two, right? Because we discarded two keys, or we discarded one, but we merged two equal keys basically. So I think that this is going to have to be usize, and in here it's gonna be okay 0. And here it's gonna be 1 as well here. And that's just taking advantage of the fact that this returns result and yada yada. We can make use of that. So here we're going to have to say entry count, and this is going to be one. We're going to just go ahead and say count. And we might not want that to be usize. We can decide that later. But here we're going to do, this is 2, right? And here it's 1. Okay, I think that's a good place to stop. And let's real quickly do a commit. We didn't do that much today. Let's see, I might not want to merge all that README stuff. I do want to stage that. We can leave that for future time. Let's add that, add that, add that. Okay. Session 8. Start merger and add an iterator over all keys in a tree. Okay. Cool. So thanks for joining. Awesome to see Greg and Creston. Hope you're still around. But otherwise, we'll see you next week. Have a great weekend.